All right, hi Breakout Room fans. Thanks for joining today's webinar. I'm really thrilled to be joined today by Taylor Steinberg. Taylor is a software engineer at Premier Inc. Taylor's going to tell us more about that, but today Taylor's going to be walking us through how to create a text mining algorithm with Python. It actually came from some just kind of prototyping work that Taylor did with the Breakout Room content. So it's kind of an exciting use case, and for anyone that's getting into data science, Taylor can give you some tips on how to get started. So Taylor, thanks so much for joining us today. And before we get started, tell us a little bit more about yourself and your role at Premier.
All right, yeah, thanks for having me on. This is great. I'm really excited.
Yeah, thanks for being here.
Yeah, so I work at Premier, which is a healthcare company in Charlotte, North Carolina. I work on a team of data scientists as a software engineer. So in my group, we try to develop machine learning and predictive models to help hospitals and other users better align with industry.
Cool. How long have you been working there?
I've been there just over a year now.
Cool. And so for people that are interested in data science and software engineering, how did you end up in a data science role?
Yeah, so in college, I studied computer engineering.
Where did you go to college?
Clemson University. Yeah. So in computer engineering, there's a lot of outside of the standard, computer science curriculum. There's a lot of work in statistics and higher level math. So in data science, there's kind of three major topics that you need. You need strong computer science skills, programming skills, you need strong statistics skills, and you also need strong business knowledge, whatever problem you're doing. So the computer engineering field, for me at least, blended really well with that. So I asked to, I like the projects the data science team was working on, so I asked to join. I got started. Yeah.
How does it compare to the expectations you had of what a data scientist is when you're going into it?
Yeah, it's interesting. Data science is I would say it's pretty ambiguous about what it really means in the industry right now. Everywhere you go, you'll probably get a different explanation of what data science is. So, over the past year since I started doing this, my own definition of what a data scientist has changed a lot. At first, I thought it was just building a lot of algorithms or implementing machine learning things, but it's actually a lot more statistical analysis and also really understanding business problems. So if you don't understand your data, you can't really develop a great model.
Yeah. So where do you think data science is heading? What are some of the newest trends you're seeing?
Yeah, I think it's heading towards just being able to building really efficient algorithms that predict very well. So all the time, people are building better and better models for predicting lots of different things. So as people start learning more about the algorithms, it'll continue to grow.
Would you consider someone, so take me, I'm not a developer or software engineer, but I can write a little bit of code and I can certainly run a linear regression. Consider that data science?
Yeah, actually. So like I said before, there's those three different things: statistics, programming, and domain knowledge. You're probably not going to be equally as good at all three of those things. So it's just having some skills and all those topics helps you become a data scientist. So usually you work on a team of data scientists, and hopefully across the spectrum, everybody fills out those skill sets. So you understand statistics or are able to implement things, and yeah, definitely.
What would you recommend for someone that wants to get into the field of start working in data science?
Yeah. Yeah, I would say, depending on what your background is, there's a lot of different paths you can take. If you're somebody that's familiar with programming and enjoys programming, investigating more machine learning algorithms and big data, distributed computing algorithms is really fun. And if you're somebody that's more interested in the business and the statistics, just taking online courses in statistics from Khan Academy or wherever else, there's tons of places right now to learn about statistics and how you can use this for data science problems.
Yeah. So do you think it's a case where it's still such a new field? Is this accurate that if you're interested, basically start teaching yourself and just go ask to start working on data science at your current company? Is it that simple?
Yeah, definitely. So that's how it happened in my company. The people in my group, we come from all different disciplines, really, and we're continuing to add more people from different disciplines. So it's really, you can really push it however you want to. If you have the interest and you're able to come up with the correct solutions, then that's a good fit.
Great, great. So tell us about what you're going to walk us through today and how this came about.
Yeah, so the algorithm, the text mining algorithm, I guess you could call it, that I'm going to walk through is called TF IDF, or term frequency inverse document frequency, which is an algorithm for finding similar pieces of text, right? So you don't really know anything about the text. They're not groups in any way, but you want to find pieces of text that are similar.
Mm-hmm. So what was the goal of the project? When you were looking at, I think you were looking at some of the content at Breakout Room and just kind of playing around with it for fun.
Yeah, so when you guys released Breakout Room, I got on there and started digging around. And one of the things I immediately wanted was the ability to browse videos that related to the one I'm watching. So, like on a lot of different video sites.
Right.
Since you guys are so new and you don't have a lot of data yet, it's hard to build a really, really strong model, but for a smaller data set, TF IDF does really well. So that's why I went into it.
I was really amazed because typically a lot of recommendation technology relies on what do users view, what are their behaviors, and what are like clustering around those behaviors to recommend.
Right.
So I like this approach that it was really from scratch. You could get something up and running that was, I thought, pretty impressive. So I'm excited to see how it works. So I guess I'll let you take it from here, Taylor. I'll give you control of the presentation.
All right, sounds good. All right, great. So TF-IDF, like I said, term frequency and inverse document frequency, right? So at a high level, term frequency, if you have a paragraph, term frequency is how often does each word in that paragraph appear out of all the words in the paragraph, right? So for every word, you get a term frequency value, and then for inverse document frequency, that's a measure of how often or how many paragraphs is this word in compared to all the paragraphs in your corpus of documents. Right? So once you have those two numbers, you basically multiply them together, and then you get what's called a TF IDF score. So when you have a corpus of text or a lot of different paragraphs and documents, you get a TF IDF score for every term in that corpus, right? And that is assigned to each document. So once you have all those, you can then do a similarity score, so which I'll go into a little bit later. But once you have the similarity score, you can basically find documents that are similar to each other. So does that kind of make sense?
Yeah, absolutely.
Okay, cool. So, so using TF-IDF on a data problem is kind of more of an art than a hard science. So there's a lot of different parameters you kind of have to play with in order to fine-tune your algorithm to best represent the data you have. So there's a lot of different things you can take into consideration, right? So if you're okay, so if you're like trying to mine some data that's like animals in a zoo, usually when you have phrases like a black bear and a brown bear, you don't want to get rid of the words black and brown. You want to keep those together. And as one single term. The other things you want to do is you want to try to get rid of common phrases like the word a and that, and then words that don't really mean anything to the paragraph. Right? So
keep all the important terms, the most relevant terms, to get rid of common terms that are just noise, right?
Right. So that process, getting rid of terms, is called getting rid of what they call stop words. Right? So if you go search around the internet for stop words, you'll find lots of different paragraphs or lists of text that have all these kind of phrases if you can pull into the algorithm. So once you get rid of all those stop words, then you can do what's called stemming. So you got rid of all those words, and all you have left is more useful words like maybe like running or acrobatics or something. And what stemming does is it would take the word running and just get rid of the end of it, the ing, and just turn it into run. And something like acrobats, it would just make acrobat, right? So you get rid of all these nuanced distinctions between all the words in the corpus of text.
Mm-hmm.
So at that point, you have a very kind of a similar representation of all the text that you're trying to mine.
Right. Excellent.
Yeah. Yep.
So that makes
Say it again.
So that makes sense.
Yeah. So so I'm gonna show you guys like the Wikipedia page on TF IDF because this is what I usually go to. It has a very thorough description of all the different parameters you can play with TF IDF. Right. So let me try to share my screen real quick.
Great.
Apologize for the infinite loop stuff that happened. Right. All right, so here's the, can you see this okay?
Yep.
Right, so here's the TF IDF Wikipedia page. If you scroll down a little bit, you'll come to the more advanced definitions of term frequency and inverse docking frequency. And if you notice over here, there's a couple different versions of calculating the term frequency, and there's a couple different versions of calculating the IDF weight, as they call it here. So these are things you want to take into consideration if you want to, say, smooth your data sets, or you don't want to give really strong correlation to words that occur really often. So doing things like, and you can research more about things like log normalization, basically minimize how different a word that appears 100 times is from a word that appears 10 times, right? So you don't necessarily want it to be 10 times more valuable. You just want it to be twice as valuable for more common words. So they do things like that. So the implementation that I have put together, I use a standard raw frequency for the TF weight, which is this, the number of times it appears in a phrase over the total number of words. And then for IDF, I use inverse frequency with smoothing. So that is usually the the best place to start, I guess. Let's see if I can stop this. Yep. We're back on set. Everything making sense so far?
Yeah.
Okay, cool. So I'll try to run this basically up to that point in the code I have written locally. And we'll just dig into the debugger and look at kind of the outcome values you get when you run TF IDF. So I'm going to run this against Breakout Room's service layer, basically their REST API there. So it took me a little while to find that, but I found it. So I'll go back to the screen sharing. All right. You can see my screen right there again?
Yep.
All right, great. So, so this code's up on GitHub right now under my account, and we'll link to that after the
cool.
Video. Yep. So basically on here, I have this TF IDF class that you give it a bunch of documents. And then the really important public method at this point is this evaluate method. So this does is it goes in and runs TF IDF, and then it finds similar text documents. So let's see, I'm going to set breakpoints at here. I have this script, so this is going to go out, make all the requests to all the pages on your website right now. Hopefully, I'm not like DDoSing you guys or something about it. Yeah. So I think there's about 20 of them out there right now. So you guys have been adding a lot of content because when I started this, there was like 15 pages of videos. Now like,
out there. Yeah.
Yep. So all right. All right. So here, can you see this okay?
Yeah, you may want to blow up your text just a little bit.
Yeah, I'll see if I can do that.
But otherwise, it's fine.
Yeah. Honestly, not sure how to blow up the debugger, unfortunately. So, but anyways, I'll try to explain it the best I can. So in here, we have one document that was loaded, and it looks to be something about jQuery and experiments and design. Basically, but you can see here that all the words from that document has a score associated with them. So, like the first word is just a dash. The second word is a design. A design has a value of 1.908, right? And the next word, EMOT, I'm guessing that was a motion that got stemmed out. That has a value of 4.42. So a higher value at this point means it's more important to the document. So another high word is experiment, which is a 4.17, right? So, and then if we keep going, so the documents, in each document for every term in it has the score, right? And, yeah. So now that we have a list of scores for every document, we can go through and run an algorithm called k-nearest neighbors, which is a pretty simple algorithm. Basically, all it does is it takes all those scores, does a similarity between them, and then the ones that are the closest together is the nearest neighbor, right? So after you run this, basically every video on the website will get a list back of all the similar videos to that one, based on this algorithm. So mentioned the similarity score, and the similarity score for my implementation, I use cosine similarity. What cosine similarity is, see if I can show you guys the code. It's pretty simple. So this first parameter, A vector, and the second parameter, B vector, those are the scores for each document. So the two document score vectors. First thing you do is you basically multiply each vector together, each value in each vector together to get a numerator value. And the second value, you take a magnitude, which is basically Euclidean distance, like a vector distance for anybody that's familiar with linear algebra or some calculus. So you take those two values over each other, you subtract one from it, and that gives you a single value, which represents how similar those documents are to each other. Still making sense?
Crystal clear.
All right, awesome, cool. So then after we run this, I'll set a breakpoint here. And this is definitely the most computationally intensive part of the algorithm. K-nearest neighbors. It's a really easy algorithm to implement, but it's a in computer science notation. It's basically an n squared algorithm. So you're comparing every element against every other element. So it can take a while to run if you have a really large data set, and that's definitely something to watch out for. You can try to implement this in the real world in production. As your data set gets bigger, it's going to take longer and longer to run on a single machine. So we'll let that run. That's still going.
So when you pull down the content from Breakout Room, where did you store the data about each page?
So I'm just storing it in memory right now. I'm not writing it out to like a database or anything, but that's definitely something you could do. So if you want to just pull it down once and just store it locally, you can. So what's nice about Breakout Room is you guys have a nice REST API that you use. So I was able just to take advantage of that. So this usually doesn't take this long. I'm just gonna run it from the top again. So I'm just gonna let it run again. Actually, I ran this earlier, so I'm just gonna open up the output file. So when I ran all this, I wrote out the results to a CSV file. So I'm just open that up. So I got wiped it out. All right, it ran again to populate it now. Great.
Oh, cool.
Can you see this okay?
Yeah, you just may want to zoom in on your text.
Yeah. Let's see.
See where it says 100%?
Oh, there it is. Yep. Not a big percent, as you can tell. Great. So here in the first column, we have basically all the videos on Breakout Room. And then these columns to the right are the most similar videos according to the algorithm I just ran in order of most similar, right? So some of these, since the data set's pretty small, like I mentioned before, some of them are more precise than others.
Right.
Definitely some things we can do in the future to make things more precise. So like I talked about, keeping really important phrases together. So something like MapReduce, right? You might want to treat MapReduce as one word if it's split it into, or instead of two different words, it's not map and reduce. MapReduce is kind of one phrase.
Right.
So things like that we can do to our data to try to maximize, our results.
Yeah, another thing we're trying to do is encourage people to add descriptions and tags to the content as well.
Right. Yeah, and the more information you have, the better the results are. Absolutely. So we'll scroll through these, see if we can find some that are good. So just the first one result we have here is energy and communities in Colombia. The second one's how the sharing in the marketplace and our sense of community. So those are in your head. You can kind of see how those are kind of similar.
Yeah, the third one seems pretty accurate though about something to do with Mexico, I believe.
Right. Right. Yeah. So in the second one, it says the artist as a startup is the title of the video. And the second one is 10 strategies for startup success. The third one, or the second one, I should say, is learn a startup. So those are pretty similar. So we can keep it on that list, but Python's usually pretty strong. So really differential words like Python and Ruby and startup, those really seem to make a big difference.
Right.
In the results. So you start noticing those things, and kind of as your job as a data scientist is to recognize those things. And then figure out how you can put those into your algorithm to make them better. Yep.
Yeah, this is really great. It's amazing just with sometimes just the title, just a few words, that it can be pretty accurate. I mean, certainly much more useful than trying to comb through all the content yourself sometimes.
Right. So I'll go look at your guys' website to show you what all the text that I use for this. So not only do I pull in the video title, but I also pull in the description. And I also pull in the, I think you guys call it your company ID.
Right.
Yep. So I pull all those things in and I concatenate them all together into one big document. is what I call it.
Mhm.
So all those things are kind of thrown in. So hopefully, you know, things that are maybe from the same company will show up together. That'd be ideal. Yeah.
Great. That's so cool. So where can people find this on GitHub?
Yeah, so my username is TDSTEIN or TD Stein. So I'll link to it. You can go onto my account and pull it down. I have it published under the MIT license right now. So everybody watching is welcome to take it, do whatever they want to it, contribute back. That would be fantastic. So one of the things I want to do in the future with it is add in all those different types of IDF and TF, so that I showed on Wikipedia. I want to add those things in to give a little more flexibility to the algorithm.
Great.
Yeah.
That's great. And were there any other models or any other considerations you would suggest people try out as well with this?
Yeah, so like I mentioned earlier, TF IDF is really great for when you don't have a ton of data or you don't know a lot about your data. You know, it's a really great algorithm as a starting point. And one of the other really distinctions between it and a lot of other algorithms is that this isn't a classifier algorithm, right? So I noticed you guys started adding tags to your website, right?
Mm-hmm.
So as people start going in there and they start adding in their own tags, you know, maybe it's Python or Java or Cydex or whatever. Once they start adding those tags, there's other algorithms like naive Bayes and decision trees,
Mm-hmm.
other algorithms like that are better at classification. So they're better at automatically generating the tags for it. Right?
Mm-hmm.
Yeah.
Great. Excellent.
Yeah.
Okay. Well, thanks, Taylor, so much for walking us through this. This is really great. I definitely encourage everyone to download the code on GitHub. Let us know what you think. And yeah, Taylor, thanks so much for being here today. And everyone watching, we'll see you next time.
Yeah. Thanks for having me on. Appreciate it.
Thanks. Take care.
All right. You too.